Hi there, welcome to this Alchemist Chemistry video where I'm going to try and prepare you for the IGCSE Chemistry Exam Paper 2. These are open source questions, but I've created a paper which will hopefully prepare you as well as possible for any eventuality in the real thing. Let's get started. This first question is looking at ethanol and is an organic chemistry question. Ethanol is a member of a homologous series. Give two characteristics of homologous series. They're molecules that have the same general formula, similar chemical properties because they have the same functional group, that is the atom or group of atoms that give chemicals their chemical properties, graduated trend in their physical properties, increasing boiling point with chain length, for example, and finally, each successive member of the family will increase in size by CH2. The next part of the question says, when ethanol is heated with potassium dichromate and one other reagent, the ethanol is oxidized to ethanoic acid. And then it says, give the formula of that other reagent. Well, that needs to be acidified potassium dichromate, so that reagent would be H2SO4 sulfuric acid. Then it says, state the colour change that occurs during this oxidation reaction, oxidizing alcohols. The colour change we'd expect to see is that it would go from orange to green as the oxidation state of the potassium dichromate changes. Okay, moving on. Draw the displayed formula or the bond shown for ethanol and ethanoic acid in the boxes provided below. So I'm going to show you those diagrams now. So ethanol has this displayed formula, CH3CH2OH, OH being the alcohol functional group, whereas ethanoic acid being a carboxylic acid, CH3CO and then OH as well. Double bond oxygen, single bond oxygen, and single bond to a hydrogen. That's the carboxylic acid group on the end there. Now, the next part of this question is quite long, looking at methods for producing ethanol. We're looking at hydration of ethene versus the fermentation of glucose. And it says, discuss the advantages and disadvantages of these two methods using the information in the table to support our answer. There's a lot we could say here. For example, we could look at this in terms of the advantages and then separately the disadvantages for each process. So the advantages for the hydration of ethene would include it's a fast, continuous process, and that the hydration of ethene produces a pure product, just ethanol. The advantages of fermentation are that sugarcane is a renewable resource. We can grow it continuously. Fermentation uses lower temperatures and pressures compared to the hydration of ethene, which is less energy intensive, and that will mean less fossil fuels being burnt to generate energy, for example. And yeast is not a toxic or harmful waste product. However, the disadvantages of these processes would be as follows. The hydration of ethene does require high temperatures and pressures. This is going to be a very energy intensive process, and therefore we are going to have to burn a lot of fossil fuels to generate that energy, and there's obviously the environmental implications of the CO2 produced by those processes. C2H4, ethene, is derived from a finite resource, crude oil. And finally, phosphoric acid catalyst is itself a corrosive waste product, which we have to manage carefully. The disadvantages of fermentation of glucose include that the use of land for the fermentation crop means that we're not using that land for food crops, for example, and that's going to be a problem if there are sort of food concerns, particularly in LEDC countries. Fermentation is a slow batch process, and finally it produces an impure product of ethanol, which is a mixture with all the other various things as well, which will require some form of separation to get the ethanol out from the mixture. And this final part of the question is looking at the fermentation process in more detail. Word equation, glucose being converted to ethanol and carbon dioxide. We're being asked to write a chemical equation, a balanced symbol equation for that reaction. First thing to get right is the formulae. The formula of ethanol is CH3CH2OH. The formula of carbon dioxide is CO2. Secondly, we then worry about the balancing. 6 carbons on the left-hand side, there need to be 6 carbon atoms on the right-hand side as well, if this was a balanced equation. By putting a 2 in front of both the ethanol and the carbon dioxide, we ensure that this is correctly balanced. Continuing the theme of organic chemistry, this next question is about esters. Ester A reacts with water to form ethanoic acid and ethanol. This is a hydrolysis reaction. The displayed formula of the reactants and products are shown in the equation below. The molar enthalpy change, or delta H, for the reaction is 0 kilojoules per mole. That'll come into play later. Draw a ring around the functional group in ester A. I have done so already. The functional group is the ester, or ester linkage, and that is a carbon double bond oxygen, single bond oxygen found in the middle of the molecule. The next part of the question is going to look at us naming that ester. So how do we go about naming esters? Well, usually we think about what parts we're trying to name. So first of all, we look at the part which is connected to the oxygen here, okay, and we look at how many carbons long that is. This is 2 carbons, that makes you think of eth, and it will end in -ile, just like the name of alkyl chains in branching. The rest of the molecule has come, well, it looks like it's come from a carboxylic acid molecule, and therefore it's derived from the naming of carboxylic acids, and it ends in O8, and it's 2 carbons long, so that is going to be ethanoate. So bringing the two parts of the name together, the name of this particular ester, based on its structure, would be ethyl ethanoate. Next, we're being asked to describe a chemical test that we can use, which is not an indicator to show that this ethanoic acid, this carboxylic acid, is present. Well, we can think what reacts with acids. Well, things that react very visibly with acids are carbonates. So we could add sodium carbonate, Na2CO3. It would fizz and effervesce as carbon dioxide gas is released. Now, the final part of this question is actually looking at energetics. It says, explain why the molar enthalpy change for this reaction is 0 kilojoules per mole. In your answer, refer to bonds broken and bonds formed. In my head, I'll be thinking of something called Bendamex. Breaking bonds is endothermic, making bonds is exothermic. Therefore, to have a 0 kilojoules per mole enthalpy change, this must be the case. The amount of heat energy taken in breaking bonds and the reactants must be the same as or equal to the amount of heat energy being given out when we form bonds in those products. It's the only way it could be 0 kilojoules per mole. Now, at this point, the rest of the question veers off into equilibrium territory. We're told that a mixture of ester A and water is left in a sealed container until the reaction reaches dynamic equilibrium, and asked to explain or describe what dynamic equilibrium is. Well, a dynamic equilibrium is a situation where the rate of the forward reaction is equal to the rate of the reverse or backwards reaction, and the concentrations of reactants and products remain constant. Do not confuse these two words in those two sentences. It's vital they are as it appears here. Next, we're being asked why adding a catalyst does not change the position of an equilibrium. Well, that's because whilst catalysts do increase the rate of reaction, they increase the rate of the forward and reverse reaction to an equal extent or by equal amounts, and therefore the position of the equilibrium will be unchanged, will not move. Next comes a calculation. We're being told that ethanoic acid produced in the reaction is completely neutralized by 22.75 centimeters cubed of 0.15 mole per liter barium hydroxide and alkali solution. So this is a concentration calculation. So first thing I would do is look at the equation we're given and make sure I note the molar ratio of ethanoic acid to barium hydroxide. Then I'd make sure I read the question really carefully. When we asked to calculate the amount in moles of ethanoic acid being neutralized, moles therefore, molar calculation, and I've got to give my answer at the end to 3 significant figures. So technique for solving calculations. First thing I'd do is write the appropriate formula triangle in the margin of the page. Moles, concentration, volume, remembering that concentration is moles per litre and volume must be converted into litres. First step is how many moles of barium hydroxide, the thing we have the most information about, are there in this experiment? Well, moles equals concentration times volume, so N equals C times V. That's 0.15, that's the concentration, times 22.75 over 1,000, converting my volume from centimeters cubed into litres or decimeters cubed, giving us 3.4125 times 10 to the minus 3 moles of barium hydroxide. Next step is called the molar ratio. What's the reacting ratio of ethanoic acid to barium hydroxide? Well, according to the balanced equation, 2 moles of ethanoic acid react with 1 mole of barium hydroxide, as I've recorded here. So if I know the barium hydroxide, to get myself to the amount of ethanoic acid it can react with, it's a multiplication of 2 to get from that 1 to 2 in the ratio. So I simply apply that ratio to the actual amount we have ourselves. So we actually have 3.4125 times 10 to the minus 3 moles of barium hydroxide. So if I multiply that number by 2, applying the same ratio to the scenario, this means it can react exactly with 6.825 times 10 to the minus 3 moles of ethanoic acid. And that is our answer, but of course that's not to 3 significant figures, so I then converted the 3 sig fig here, 6.83 times 10 to the minus 3, or in other words, 0.00683 if it's not in standard form. The final part of the question is looking at condensation polymers, and it's a polymers question. We're given 2 monomers, a dicarboxylic acid and a diol. We're then being asked to give the repeating unit of the polymer form. So this involves condensation reactions, elimination reactions, in which the OH group is removed from the dicarboxylic acid and the hydrogen is removed from the alcohol functional groups of the double alcohol, and then we just join the 2 monomers together at those points. So imagine removing these from the scenario and then just bolting what remains together. If you do so, what you'll end up with is this. Okay, you can see that the OHs are gone and the hydrogens are gone. I've just simply linked the 2 remaining fragments of molecules together. These continuation lines are called empty bonds. That's to show continuation of the polymer chain for a long duration. The square brackets encapsulate the repeating unit, so we can say that it repeats many, many times. And the N written after the repeating unit is emphasizing that this repeating unit will repeat on many times over and over again. Carrying on the paper 2 journey, we're now going to look at extraction of metals, metals in general, and even alloys. This part of the question is about extraction of metals. We're given a list of metals, and the first question is identify the metal from the box above which burns with a bright white flame or a bright white light. That would be magnesium. If you've ever done that experiment, it's very, very bright indeed. You often have to put some blue glass in front to protect yourself. Now, next it says, in the earth, metals are found in ores, which are compounds, or as uncombined elements. Explain which metal from the box is most likely to be found as an uncombined element. So we're looking for the element in this box which is most unreactive, and that would be silver. And that's exactly the reason why we find it as a native metal in the Earth's crust. So our answer is silver. It is the least reactive of the metals present. So unreactive, in fact, that it will probably not easily form oxides by reacting with oxygen in air. Carrying on the theme of extracting metals, we're then given a section of the reactivity series with 4 metals, being asked which method would be best to extract these metals from ores, either heating the metal oxide with carbon or using electrolysis. We may be asked to explain which method would be used specifically to extract lead from lead to oxide from PbO. I've actually put in myself where carbon would be in this particular reactivity series. Carbon is actually between aluminium and zinc in reactivity. So you can see that lead is definitely below carbon in the reactivity series. So that means that it's going to be able to extract the lead from lead oxide. And that's what our answer is going to hinge upon. So I've said here, it's quite a wordy answer, I'll go through it all. So lead is below carbon in the reactivity series, therefore extraction by heating with carbon would be a suitable extraction method. I've then written lead oxide plus carbon goes to lead plus carbon dioxide. I've written a balanced equation supporting that. But actually, there are different ways in which carbon could do this, and it's just equally valid to say that lead oxide could react with carbon to form lead and carbon monoxide, because still the carbon is the reducing agent and doing the job of extracting the lead from the oxide. Now we're going to look at metals and alloys in greater depth. We're told that aluminium is a malleable metal that conducts electricity. We're given a diagram of a giant metallic structure minus the presence of delocalized electrons. I don't want to give that away too early. Explain why aluminium is a malleable metal, what malleable even means. Might be useful as well. So malleable means that the metal is easily shaped and can be molded into different shapes. And the reason why metals can do this is because they have layers of metal cations that can slide over each other without breaking the strong metallic bonds between those metal cations. The next question is, explain why aluminium is able to conduct electricity. I did mention delocalized electrons a second ago. Well, it's because aluminium, like all metals, has delocalized electrons within its structure, and those delocalized electrons are able to flow freely throughout the structure and therefore conduct an electrical current. And finally, it says aluminium cannot be extracted by heating with a mixture of carbon and aluminium oxide. Give a reason why heating aluminium oxide and carbon does not produce aluminium. Well, going back to our original reactivity series, it implies that aluminium is probably above carbon in the reactivity series. So if aluminium is higher in the reactivity series than carbon, and it is more reactive than carbon, carbon will be unable to extract aluminium from aluminium oxide. This final question on the metals and alloys theme is the alloys question. So we're given the structure again of a pure metal. It says metals are often made into alloys, make them harder. Explain why alloys are harder than pure metals. Draw a diagram to support your answer. I've drawn my diagram first. The diagram has to be labelled and annotated to be worth marks. You can see here's my regular metal structure with the cations of the same size, but I've placed a different sized atom mixed into this structure, embedded in this structure, and it is currently disrupting these regular layers of metal cations. And that's exactly how alloys work, and my follow-up answer is going to really refer back to this diagram. Okay, so first of all, what is an alloy? An alloy is a mixture of a metal with a different element. Could be another metal, could be carbon. Different sized atoms, like the one I showed above, disrupt the regular arrangement of the layers of metal atoms or cations, depending on which way you're approaching this. I would probably refer to them as cations, because that would link back to giant metallic structures as well. This prevents the layers of metal cations from sliding over each other easily. This results in the alloy being harder than the pure metal, as pure metals have layers of metal cations that are the same size, and so their layers can slide easily over each other. So the different sized atom disrupts the regular arrangement of the metallic structure, prevents those layers of similarly sized metal cations from sliding over each other and results in a more rigid and hard structure as a result. Now we're going to look at the much maligned solubility topic, particularly solubility curves. So this question is about solubility, and I'm going to show you a graph which is comparing the solubility of copper 2 chloride with sodium chloride at different temperatures being dissolved in water. You can see there's these curves on our y-axis. We have the solubility in grams of solid being dissolved per 100 grams of water. And on the x-axis, we have the temperature increasing in degrees centigrade. The first question is, determine the temperature at which copper 2 chloride and sodium chloride have the same solubility, and show on the graph how you obtained your answer. So I've looked for the crossover point between the two curves, which is right here. So I've drawn my line down to the temperature, and I can see that where that crossover point where they have equal or even solubility is at 56. So the answer is 56 degrees centigrade. The next question, a saturated solution of copper 2 chloride has the maximum amount of copper 2 chloride dissolved at that particular temperature in 100 grams of water is cooled from 40 degrees to 10 degrees. Determine the mass in grams of copper 2 chloride that will crystallize out. Well, all we need to do there in this time, again, I've shown it very clearly on the graph by drawing things on. I've found where 40 degrees is, and I've drawn a dashed line up to the copper 2 chloride line and then across, and I found that at that point it would be able to dissolve 31 grams of solid. I then found the other temperature, 10 degrees, drew a dotted line up to the curve and across, and I found that at that point it'd be able to dissolve 13 grams per 100 grams of water. So therefore, if you drop the temperature from 40 to 10, the difference would be, the difference in those two numbers, 18 grams of solid should crystallize out as the solubility of the solution drops as the temperature drops. So it's the higher temperatures amount minus the lower temperatures amount of solid dissolved tells us how much of that solid should crystallize out. Up next, we have a bit of an experimental question. The student uses this method below to determine the solubility of potassium chloride in water at room temperature. Record the mass of an empty evaporating basin. Pour some saturated potassium chloride solution into the evaporating basin. Record the mass of the basin and the solution. Then heat the basin to remove all the water from the solution. Then re-record the mass of the evaporating basin with a dry potassium chloride once all the water's gone. They recorded their data in a table like so, and they're being asked to calculate two things. First, calculate the mass of dry potassium chloride obtained. Well, that would be by taking the mass of the evaporating basin and the dry potassium chloride and taking away the mass of just the evaporating basin itself. So you're left with what mass is just the dry solid. So 36.2 is the mass of both the evaporating basin and the dry solid. 58.1 is the mass of just the empty basin. And that means that the mass of salt inside the basin is therefore 5.1 grams, recorded here. This is calculate the mass of water removed. This time, different calculation. This is the mass of the evaporating basin and the water and potassium chloride. And this is the evaporating basin and the dry potassium chloride. So we're taking away the mass of the evaporating basin and the potassium chloride, which has still got water, and take away from that the one which hasn't got water. You're left with the difference, which would be 15 grams, which means that 15 grams of water was removed when you heated the saturated solution to form the dry potassium chloride. Just got to make sure you read this table really carefully. This final part of the question can really confuse students if they're not careful. It says calculate solubility of potassium chloride in grams per 100 grams of water. This question may never have been seen before by students, and they might not really know how to tackle it, but actually it's all linking back to the previous section. We have just found out that if we evaporate or remove 15 grams worth of water, it left behind 5.1 grams of our potassium chloride salt crystallizing out. So now what the question is basically saying is, well, what's the solubility per 100 grams? Basically scale things up to 100 grams worth of water. So if we know how much will dissolve in 15 grams of water, because it came out when we heated it, we can scale it up to, what if we had 100 grams of water? So we divide 100 grams of water by 15 grams of water from the previous question. That's 6 2/3 times greater. Okay, so if we times the mass that crystallized out from the previous section by that 6 2/3, we find that 100 grams of water should be able to dissolve 34 grams of potassium chloride. It's really important just to think back to the previous question. This final section is, why would the student's method not be suitable for determining the solubility of hydrated copper 2 sulfate? Well, unfortunately, if you heat hydrated copper 2 sulfate, it stops being hydrated copper 2 sulfate. You will unintentionally also drive off the water of crystallization, which is part of the ionic structure itself, leaving behind a different compound altogether, which is anhydrous copper 2 sulfate, which was not the thing you were trying to experiment with in the first place. So you've got to think about the fact that hydrated salts are quite sensitive to heating. Rolling on, guys, and if you're sticking with this, really well done. We're now going to look at Group 1 metals and also moving on to their reactivity. Okay, so a teacher adds a piece of sodium to a tank of water with some universal indicator, and they've got the equation for the reaction taking place, and they've told us that the sodium floats on the surface of the water and that the universal indicator changes colour. We'll come on to the colour later to show that an alkaline solution has formed. We've got to give two other observations other than that the sodium is floating. We're mainly focusing on the metal here. So the other observations I'd be thinking of might include the fact that the piece of sodium will move as a molten ball because the melting point of the sodium is so low that as it is heated, it will turn into a molten metal. It shrinks and disappears over time as it forms an aqueous solution as a product. And finally, it will fizz and effervesce due to the generation of a rapid generation of hydrogen gas. And the reason why it's moving on the surface of a molten ball is the hydrogen gas will cause the piece of metal to spin on the surface of the water. Now, next we've been asked to give the final colour of the universal indicator. Well, we know that we're forming an alkali, quite a strong alkaline solution. Therefore, the colour we'd expect would be purple. Trying to avoid blue, definitely purple. The question continues to look at the electrical configuration of a comparison between two group 1 metals, and eventually talks about their reactivity. The diagrams below represent an atom of lithium and sodium respectively. Give a reason why lithium and sodium have similar reactions with water. It's all to do with the outermost electrons, okay, or in this case electron. So they are both group 1 metals and have one electron in their outermost or valence shell, which will dictate their reactivity. Then the question expands upon that and asks us to think about explaining why lithium is actually less reactive than sodium. It's all again down to the size of the atom and the proximity of the outermost electron to the positive nucleus. But I'll go into the full detail in my answer here. So, lithium has a smaller atomic radius, or is a smaller atom than sodium. Lithium has fewer filled inner electron shells than sodium. Therefore, the distance of the positive nucleus to the outermost electron will be smaller or shorter in lithium than sodium, and there will be less electron shielding, nullifying the influence of the positive nucleus on the outermost electron in lithium compared to sodium. So the attraction of the outer electron to the positive nucleus would be greater in lithium than in sodium. And this will mean it is harder for lithium to lose its outermost electron compared to sodium, making lithium less reactive than sodium comparatively. More than halfway through, guys, and now we're going to look at a calculations section. This first calculation is going to relate to the molar volume of a gas. So the teacher adds 0.15 grams of lithium to an excess of water and collects the hydrogen gas produced. The equation is given to us. The teacher collects 254 centimeters cubed of hydrogen gas at room temperature and pressure, very important. Show by calculation that 1 mole of hydrogen gas has an approximate volume of 24,000 centimeters cubed at room temperature and pressure. That actually is the molar volume itself. So we're going to try and do a proof for the molar volume quantity. So thinking about this, first thing I did was I wrote down the triangle for the mass-mole conversion. Moles is mass over relative mass. And I thought where my starting point would be. I thought lithium would be a good starting point because I have its mass. So the first thing I did was work out the moles of lithium from the question. So moles is mass divided by relative mass. 0.15 grams of lithium divided by 7, the mass number, and therefore the relative mass of lithium from the periodic table, gave us 0.0214 moles of lithium being used in the experiment. Now, according to Banner's equation, 2 moles of lithium always react to form 1 mole of hydrogen according to this equation. So that's our molar ratio, 2 to 1. So to get from 2 to 1, I have to divide by 2. If I divide the number of moles we actually have in our experiment, which is 0.0214 by 2, to find out how many moles of hydrogen it can actually form, it's only going to be 0.0107. So how does this relate to 1 mole's worth of hydrogen? Well, it's much smaller, isn't it? So if I divide number 1, which represents 1 mole of hydrogen, by the amount of hydrogen we actually have in the experiment, which is the very small number, 0.0107, it's about 93 1/3 times bigger. So if I multiply the volume of gas we were able to collect, which represents a very small molar quantity of hydrogen, by that quantity, that multiplication factor to get it up to as how much we'd need for 1 mole's worth. So 254 from the question times 93.33, how many times bigger we need to get it to. We come out with 23,707 centimeters cubed. Now, great thing is that is very close to our approximate value of 24,000 centimeters cubed, which is what we're looking for in the question. So we've just solved our problem. Next, we come to the dreaded titration and titration calculations, but don't worry, guys, we're going to get through this. A student does a titration to find the concentration of a solution of dilute sulfuric acid. The student uses the solutions and the following apparatus: dilute sulfuric acid, potassium hydroxide, which is an alkali with a concentration of 0.240 moles per litre, methyl orange indicator, and finally these 3 pieces of apparatus: a conical flask, a 25 centimeter cubed pipette, and a 50 centimeter cubed burette. The student wants to find the volume of sulfuric acid needed to neutralize 25 centimeters cubed of that sodium hydroxide alkali. Describe how the student could do this titration. Assume that all pieces of apparatus are clean and dry already, so you can skip that step. So I've gone into a blow-by-blow, step-by-step, very clear method for how to carry out an effective titration. First, let's deal with a pipette. You would use a 25 centimeter cube pipette to collect exactly, ideally, 25 centimeters cubed of the potassium hydroxide alkali at eye level with the bottom of meniscus, that's the air pressure bubble, on the line of the pipette itself. Then you would add that to the conical flask. You then add a few drops of methyl orange, the suitable indicator, to the conical flask initially. Secondly, you then fill the burette, the big long piece of apparatus, with the sulfuric acid to 0.00 centimeters cubed at eye level, ensuring that the bottom of the meniscus, again the air pressure bubble, was on the line of 0.00. You'd slowly add the sulfuric acid using the tap into the conical flask while swirling the conical flask continuously until you saw a permanent colour change in the methyl orange. This would mean it would go from yellow, alkali conditions, to red, acidic conditions. You record the volume of the acid added from the burette to 2 decimal places, again at eye level. You then repeat the titration multiple times over, slowing down to near dropwise addition as you got close to the volume you originally recorded up here. And then you'd obtain something called concordant results. That's 2 results at GCSE that are within 0.2 centimeters cubed of each other. You then take an average of those results and do your concentration calculation. With the experiment covered, we can now come to the calculation itself. The student needed 15 centimeters cubed of sulfuric acid to neutralize 25 centimeters cubed of the potassium hydroxide alkali. Here's the reaction taking place: 2:1 ratio of alkali to acid. Calculate the amount in moles of potassium hydroxide, the alkali, in the 25 centimeters cubed of potassium hydroxide solution of concentration 0.240 moles per litre. So what I would do, again if it was me, is I'd initially straight away write my formula triangle, my appropriate formula triangle for concentration in the corner. Moles is concentration times volume, remembering that volume is measured in litres, not in centimetres cubed. We're trying to work out moles, so moles equals concentration times volume. There's my concentration from the question. There is the volume in the question divided by 1,000 and convert it from centimetres cubed into decimeters cubed, giving me 6 times 10 to the minus 3 moles of potassium hydroxide present in the experiment. Unsurprisingly, the next thing they want to work out is the amount of sulfuric acid in the 15 centimeters cubed of acid itself. That's going to be using the molar ratio, okay, comparing what we now know to the unknown. So the molar ratio from the balanced equation is a 2:1 ratio of potassium hydroxide to sulfuric acid. So I've simply re-recorded that down here. And I know to get myself from 2 to the 1, we know the 2, we don't know the 1, I have to divide by 2. So if I now divide our known moles of potassium hydroxide, which is 6 times 10 to the minus 3, by 2 as well, following the same molar ratio, I get 3 times 10 to the minus 3 moles of sulfuric acid it will be reacting with. Now, we're going to eventually turn it back into a concentration. So now we know the moles of sulfuric acid. We're going to convert it into concentration in moles per litre. That comes back down here. I've rewritten my formula triangle again, just in case I forgot it. This time I'm doing concentration. Concentration is moles over volume. So 3 times 10 to the minus 3 is our moles divided by the volume in litres or decimeters cubed. 15 divided by 1,000 to convert the centimeters cubed into decimeters cubed gives us 0.2 moles per litre of sulfuric acid used in the experiment, which is what I've recorded as my answer down here. Always write the formula triangle in the margin, guys. It really, really helps. Just before we get on to the final straight, we're going to look at electrolysis and energetics. I have one more contextualized molar volume calculation, which is a really nice one to see because it also involves using tons in the question. So this question is about the manufacturing of sulfuric acid, in step 1 of the process, sulfur is burned in oxygen to form sulfur dioxide gas. The equation is shown here. State 1 environmental problem caused by the release of sulfur dioxide into the atmosphere. That would be acid rain, because when the sulfur dioxide reacts with water and moisture in clouds, it forms a form of sulfuric acid, then falls as acid rain and causes all of the unfortunate problems associated with acid rain. On to the question itself, which is the big chunky calculation. So a mass of 6.4 tons of sulfur is burned to produce sulfur dioxide gas. Calculate the maximum volume in litres or decimeters cubed of sulfur dioxide gas that can be produced at room temperature and pressure. We're told about the molar volume being 24 litres or decimeters cubed. We're also told that 1 tonne is 10 to the 6 or a million grams. We have to make sure we give our answer in standard form at the end, which we definitely will. So the first thing I do, as always, is write the useful formula triangles I'm going to use in the margins. This time I'm going to have to use 2. I'm going to use the mole mass conversion triangle and separately the molar volume triangle, which relates moles and the molar volume value itself. So moles times 24 litres gives us the volume of gas. We're going to use both of those at different points. Firstly, what would I do first? I would convert my 6.4 tons of sulfur into grams, which I could then use in my mole mass conversion triangle. So 6.4 tons times a million, or 10 to the 6, is 6,400,000 grams of sulfur. Loads of sulfur. The moles of sulfur, moles is mass divided by relative mass, would be 6,400,000 grams divided by 32, the relative mass of sulfur, which is 200,000 moles of sulfur. It's a 1-to-1 ratio of sulfur to sulfur dioxide in the balanced equation, so I can just therefore assume that I also would form 200,000 moles of sulfur dioxide. And if I times 200,000 moles by 24, the value of the molar volume value, then it tells me that that will occupy a volume of 4,800,000 litres, or decimeters cubed, of volume of space. So not as scary as the question initially may have seemed. Just finishing off this question, it goes into equilibrium territory a little bit. So in stage 2, sulfur dioxide reacts with oxygen to form sulfur trioxide, and it is a reversible reaction. The yield of sulfur trioxide is approximately 98%. That's a really good yield. A catalyst is used in this reaction. Explain how a catalyst increases the rate of reaction. Explain, not describe. So, catalysts provide an alternative reaction pathway which itself lowers the required activation energy for the reaction to proceed. The temperature is kept constant. Give a reason why increasing the pressure would increase the yield of sulfur trioxide. This is a Le Chatelier's principle and equilibrium question. Okay, so if we increased the pressure, the position of equilibrium would move to the right-hand side, because the right-hand side of the equation has the fewest moles of gas, 2 versus 3. 2 and 1 is 3, 2 is just 2. So the position of equilibrium would move to the side with the fewest moles of gas, which is the right-hand side, to increase the yield of sulfur trioxide, according to Le Chatelier's principle, which is an opposition or minimalization of change theory. It then says, so that's why it is not necessary to increase the pressure, even though, according to Le Chatelier's principle, it should improve our yield. Well, the yield is already 98%, which is already suitably high enough, and messing around with pressure may add an unnecessary expense to the process. Finally, in stage 3, the sulfur trioxide is reacted with concentrated sulfuric acid to form something called oleum, H2S2O7. The oleum is then added to water to form concentrated sulfuric acid to complete the chemical equations, balanced chemical equations, for these two reactions. You've got to just basically read this really carefully and convert these words into actual formulae down here. So, sulfur trioxide is reacted with concentrated sulfuric acid to make oleum. The oleum is then reacted with water to form more sulfuric acid. And I realised that I had to have 2 sulfuric acids here because I had so much hydrogen and other things on this side. It wouldn't have made sense to have just one. So that's why the balancing number was required, the coefficient, to make sure I had equal numbers of atoms of different kinds on either sides of the equation arrow. That's just an application of words into formulae scenario. Finally, a percentage by mass question. Okay, so sulfuric acid is reacted with ammonia to form ammonium sulfate. Calculate the percentage by mass of nitrogen in ammonium sulfate, and you're given the relative mass of ammonium sulfate there. Okay, so basically what it's saying is what's the relative mass of nitrogen compared to the rest of it? So there are 2 nitrogen atoms in this formula. So the relative mass of 2 nitrogens versus the relative mass of all of it together, times by 100 to convert percentage. 28, that's the mass of the nitrogen in the molecule. 132 is the relative formula mass of the whole compound unit itself, times 100, converts into percentage. It's got 21.2% nitrogen percentage by mass. This next question is a salt preparation question. Now, there are only 2 salt preparations that are unique to paper 2, and this is one of them. This is the precipitation salt preparation method. So a teacher prepares an insoluble salt, lead to bromide, by mixing 2 solutions, lead to nitrate, an aqueous solution, and sodium bromide, an aqueous solution. Describe what the teacher should do next to obtain a pure dry sample of lead to bromide. So when the 2 solutions mix, they instantly form a precipitate, a solid. So the first step would be to filter to collect the insoluble lead bromide precipitate or solid. Once that solid has been collected in the filter paper, you would then wash that lead bromide solid in the filter paper with some distilled water to hopefully remove any soluble impurities that were clinging to those solid particles, and then eventually you would try and dry out that lead bromide in a desiccating oven or with some suitable drying method. A warm place, dabbing it with paper towel, something's going to remove the moisture, leaving it to dry until you have your pure dry sample. Next, the question transitions into electrolysis territory. The teacher sets up a circuit in a fume hood fume cupboard of pure dry lead 2 bromide solid, okay, and they connect some electrodes to a battery and to a bulb and stick those electrodes into our solid in a crucible. Explain why the lamp would not light when they placed it simply into the solid lead 2 bromide. You've got to think about this in terms of structure and bonding. Okay, so lead bromide is an ionic compound. The ions in the ionic solid are unable to flow or move. They're being held in place by the strong electrostatic force of attraction between the opposite charged ions in that solid. They can't conduct electrical current if they're not moving, and therefore nothing's going to happen. However, the teacher then heats it up and the ions can flow and move, and it does conduct a current. So when the lead bromide is molten, the lamp lights and bromine forms at the positive electrode over here. State what observation will be made at the positive electrode. We're going to see as that happens. You're probably going to see orangey brown fumes as bromine is being produced. That's why it's in the fume hood, because that's also toxic. Next, we're being asked to explain how bromide ions in the molten lead bromide become bromine molecules at the positive electrode. How does that process take place? Well, think about it like this. The bromide ions are negative. They are going to be attracted towards and move towards, migrate towards, the positive electrode, known in this case as the anode. Once those negative ions arrive at the anode, they're going to be losing their electrons to that positive electrode. This is known as oxidation. So the bromide ions are going to lose electrons until they turn back into atoms, basically, and lose those electrons to the positive electrode. The half equation kind of describes that process. 2 bromide ions are going to the positive electrode and becoming bromine molecules because they're losing 2 electrons. Electrons written on the right-hand side of half equations are being lost. Once those bromine atoms come into being in situ, they are going to join together to form diatomic bromine molecules. Here are 2 bromine atoms with their unpaired electrons here and here. More stable if they pair up, share a pair of electrons to form a covalent bond, making bromine molecules, which is our orange-brown fumes being produced. Finally, we're being asked to write an ionic half equation for the reaction that takes place at the negative electrode, known as the cathode. Include state symbols. Again, in my mind, the half equation tells us the redox story of what was going on. So if I read it through, the lead 2+ ion arrives at the negative electrode and gains 2 electrons and becomes a lead atom. That's what the half equation is trying to tell us. Here we are on the final few pages. We have some energetics and then a little bit of electrolysis to finish. So this reaction is between hydrogen and chlorine. We're told it's exothermic. We're given the equation and we're given the energetics. State the meaning of the term exothermic. Exo means outwards. So an exothermic reaction is a reaction that gives out heat energy to its surroundings. We're then given some data. These are mean or average bond enthalpies. So the table gives you the bond energies for hydrogen-hydrogen and hydrogen-chlorine bonds. Use the equation and information in the table to calculate the energy of the missing chlorine ClCl bond. Okay, so what I've done is I've drawn out my standard approach to a mean bond enthalpy calculation situation, which is like a table. Okay, breaking bonds endothermic, making bonds exothermic, and I've written out the equation again with the displayed formulae. We have 1 times HH bond being broken and 1 times ClCl bond written as X, so we don't know what it is, being broken. We also have 2 HCl bonds being made. I've written 2 times the energy to do that. These are the sum of the energies here. So 436 plus own minus 862 will equal our answer. So 463 plus don't know minus the MEX, the making bonds exothermic process, which is the 862, equals minus 184 kilojoules total of reaction. Therefore, if we bring this over the equal sign, if we do minus 184 plus this number here, 862, minus this number here, 436, we're left with X. That means X is equal to 242 kilojoules per mole. Bit of a weird mean bond enthalpy calculation there, but the table structure really works for any bond enthalpy calculation. Carrying on. Okay, so last couple of pages we're going to carry on with. Explain why this reaction is exothermic in terms of bond making and bond breaking. Again, we're going to need to apply our knowledge of Bendamex here. Breaking bonds is endothermic, making bonds is exothermic. And if this is exothermic, it's going to have to be giving out more energy than taking in. So my full answer would be more heat energy is being given out, making bonds in the products, than is being taken in, breaking bonds in the reactants. Hence, overall, the reaction must be exothermic in nature. And we're being asked to construct an energy profile diagram to represent this reaction and place in the enthalpy change arrow and the activation energy arrow as well. we were given this axis here and this starting line. So I've added the x-axis, which is progress of reaction. I've added a second line down here, which is where our products would be. So that's where the 2HCl would be. And you can see that they are lower in energy than the original reactant, so it's definitely an exothermic process. So the enthalpy change is negative. So we have a lower product line than reactant line. That's essential for an exothermic energy profile diagram. We have the arrow connecting the reactant line and the product line, which is going down, essential for an exothermic energy profile diagram. And finally, this is the energy profile itself. And this hump we have to get over for the reaction to happen is the minimum energy required for the reaction to occur, which we know as the activation energy. So I draw another arrow up to the very top of this peak, and I've labelled that EA, which stands for activation energy, which is the minimum energy required for the reaction to occur. The final question is electrolysis, and it's actually electrolysis of solutions. So here we have someone electrolyzing a solution of sodium chloride. The challenge there is there's more than two ions involved. There's the sodium ions and the chloride ions from the sodium chloride. There's also hydrogen ions and hydroxide ions from the dissociation of water. So all those things involved. We're being asked to write two half equations for what's going on at the positive and negative electrode to identify the two gases. One of the gases was giving us a squeaky pop test. That's going to be hydrogen gas. The other one is chlorine. We'll find out shortly. So look at the anode first. So the positive electrode is the anode. It's going to be attracting the negative chloride ions towards it. The chloride ions migrate towards the positive electrode. When they arrive, they are oxidized. They lose electrons to it to form chlorine gas. And if we were testing that chlorine gas, we'd use blue litmus paper, which would turn white or bleach white in the presence of the chlorine gas. Now, at the negative electrode, the cathode, two ions will migrate there, both the hydrogen ions from the water and also the sodium ions, which were in the solution as well. But because the sodium ions are more reactive, they tend to stay in solution. The less reactive hydrogen ions tend to come out of solution and actually interact with the electrode correctly. So they will collect the electrons. They are reduced to form hydrogen gas. So two positive hydrogen ions gaining two electrons to become hydrogen gas at the negative cathode. And that would correspond with our squeaky pop test, confirming it was hydrogen gas. And that ends our study of this paper 2 material. I really hope it's helpful for the actual exam. This was a crash course on as much content as possible. And if you like the video, please give it a like. And if you would like to see more of the content we make in chemistry, then please feel free to subscribe to the channel. It makes a huge difference to me when you do. Really hugely appreciate it. It helps to push me forward to make more videos like this. So, hey guys, best of luck. Hope it goes well. And you can do this. Cheers. Bye now.